Good evening, everyone. Welcome to another fun-filled and informative discussion for those who are interested in helping create a space ecosystem, industry and community within New Zealand. We've got quite a resurgence of interest in space technologies, capabilities and exploration, and I'm sure we're all really intrigued by the discussion we're going to have tonight. So thank you for helping us find like-minded enthusiasts within Wellington and New Zealand, and of course, thanks to Zoom, an international community as well. Just a quick shout out to both Eric and Emmeline for the continued support, both from a space-based perspective and from a very community-orientated perspective. And thank you for letting us beg, borrow and steal some of your resources again. We appreciate it. Just a couple of ROE, rules of engagement. We've all done these before, just as a general courtesy. Please remember to mute your mic unless you are the person speaking. And we will have a question and answer session at the end. You are welcome to ask your questions via the chat function, or we can also open it up a little bit more broadly when we get to the end of the speech. And now I will hand things over to Lindsay Parker.
Thank you. So I welcome everyone and thanks for joining. I am happy to introduce tonight's speaker, Dr. Stephanie Lowry. She was born and raised in Wellington and received a bachelor's degree with honours in Logic and Computation and a master's degree in Computer Science from Victoria University. She completed her PhD in 2014 at the Queensland University of Technology, or QUT, in Brisbane. Her thesis was Visual Place Recognition for Persistent Robot Navigation in Change Environments. She was awarded the QUT Saganto Foundation Medal in 2015 as an outstanding engineering PhD graduate. She worked as a postdoctoral research fellow at the ARC Australian Centre of Excellence for Robotic Vision at QUT. She has published extensively and received hundreds of citations for her work. She is currently a postdoctoral research fellow at the Centre for Applied Autonomous Sensor Systems at Örebro University, Sweden, where she lives with her family. Some of her research titles include improving localization accuracy using submaps in warehouses, local geometric support for high outlier spatial verification, unsupervised generation of observation likelihoods for probabilistic localization in changing environments, distance metric learning for feature agnostic place recognition. Tonight she'll present on the challenges of autonomous navigation on Mars, how the Mars rover programs have overcome these challenges, and the lessons learned. As said, you're welcome to type your questions into Zoom chat any time, and we'll try and read out as many as we can in the Q&A session after the presentation. Thank you, Dr. Lowry. Over to you.
Great, thank you very much. Yes, thanks for joining me. Thank you for inviting me as well, Lindsay. As Lindsay said, I'm going to speak on the autonomous navigation on the Mars rovers, and I'm a researcher in mobile robotics with an interest in autonomous navigation. Full disclosure, I am having some small technical problems at my end, so I may have to switch between applications to show movies. Please bear with me. Hopefully it won't be too much of a problem. So what I'd like to talk about today in this talk. First of all, I just want to introduce the Mars rovers. Then secondly, I want to talk about the different components on the Mars rovers that contribute to the navigation system. Then I'm going to talk about the navigation process itself for the Mars rovers. And finally, I am going to talk about the future of the Mars rover program. As it happens, this is looking really exciting. There is actually a new Mars rover launching in a month. So July 2020, the next generation of Mars rovers is scheduled to launch. So it looks like the Mars rover program will be continuing and getting brighter and moving forward. So the first generation of the Mars rover was the Sojourner robot, which landed in 1997. It was about the size of a microwave. It was about 11.5 kilos, around 65 centimeters, and it was scheduled to operate on Mars for about 7 days. It ended up operating for about 3 months. And in that time, it traveled 100 meters. This image is taken from its base station, the Mars Pathfinder, showing the trajectory of Sojourner around its base station over those 3 months. Now, this was very historic moments. This was the first time that there had been a mobile vehicle on another planet that was not driven by humans, and that it was driving around, that it was sending photos back from the surface of Mars. It was quite a first, and quite an exciting first step. The next generation landed in 2004. Now, it was considerably bigger than Sojourner. There were two. There was Spirit and Opportunity. They weighed 175 kilos, so they were already 15 times heavier than the little 11 kilo Sojourner, and they were planned to have a 90-day mission. The first Spirit, actually, its mission continued for 6 years, and in that time it traveled more than 7 kilometers. And the second Mars exploration rover, Opportunity, actually operated for 14 years, and in that time traveled over 45 kilometers. So having gone from 100 meters to the next generation traveling 45 kilometers was quite a dramatic step up in terms of the distance covered and the length of time that was operational. Then in 2012, the Curiosity rover landed. So this one was even bigger. It went from being 175 kilograms to being 900 kilograms. So we're talking about the size of a car. And it was about 3 meters in length. So even more, even larger than the previous one. And it's been operational for 8 years, since 2012. It's still operational. And thus far, it has traveled over 21 kilometers. So that's not quite as far as Opportunity. A couple of reasons for this, one of which it's only been operational for 8 years, not 14, so it's got a way to go. And simply, it's been doing a lot of other science along the way. So it's not just focusing on driving as far as it can. As fast as it can, there's a lot of projects and science and experiments that it's doing. And then the navigation is there to allow those science experiments to be achieved. As I said, the next generation of Mars rovers is launching in July, next month. This is the Perseverance rover. And at the end of the talk, I'll talk a bit more about what is expected from that in terms of the navigation systems. There's actually another rover also launching next month, and that's from the Chinese Space Administration. Now, I don't know anything about this rover, but this is quite an interesting development because it means there might be a new family of Mars rovers starting out into the future. So that's quite interesting news, interesting future there as well. So those are the Mars rovers. And as I said, what I like to talk about now is the different components on the Mars rovers that contribute towards the navigation. So I'm going to discuss the Curiosity rover mainly because it's the latest. It's the one that's still currently operational. There's a lot that is very similar between the different generations of Mars rovers. As you would expect, space robotics is going to be quite conservative. So things that have worked are maintained and onto the next generation. And mostly the changes that have occurred are quite incremental. So just improving what's already there rather than radically changing it. So first of all, the Mars rover's very distinctive chassis and wheel configuration is known as the Rockerbogie System. It's 6 wheels, and this is something that they've stuck with despite the fact that they've gone from an 11 kilogram Sojourner robot up to 900 kilogram Curiosity. They have maintained the same design of this system. So it's obviously something that's been quite successful. This is designed to be very stable. So the wheels and the differential are set up so that The idea is that even if the robot is tilted up to 45 degrees, it shouldn't tip over. And it's also designed to be able to get over obstacles that are a lot bigger than its wheels. So this is the Curiosity prototype. These wheels are about 1/2 meter in diameter. They're about 50 centimeters. And the idea is that it should be able to climb over rocks that are higher than that without tipping over the rover itself. Another thing that's really important when you're talking about space robots is the communication system. So depending on where Mars and Earth are relative to each other, they can be up to 22 minutes delay in sending communications back from Mars. It can be as little as 4. Of course, when you're doing something like navigation, you not only have to send information, you also have to receive information. So it can have a round trip of about 44 minutes. This is obviously going to change the kind of navigation that you do with your robot. You cannot, for example, drive it like a remote controlled car. Another more significant issue even is that to communicate, they rely on the NASA Deep Space Network. Now, the Deep Space Network is has got 3 sites around the world in California, Spain, and Canberra. And the idea is that these are distributed around the globe in such a way that no matter which direction the Earth spin is you have coverage of any direction. And it's these large radio telescopes. However, it's very popular. There's a lot of space missions and there's a lot of competition for using this. So the rover team typically can talk to their rover, can give it instructions once a day, simply because they need to liaise with the logistics of all the other missions using the communications facility. They may be able to get data from the rover 2 to 4 times a day. So this really affects the way that the navigation plan is structured. So each day, at the start of the Martian day, they send instructions up via the Deep Space Network to tell the robot what to do that day. The robot then executes these instructions, or it attempts to execute these instructions. And at the end of the day, or throughout the day if possible, sends data about what it's achieved back to Earth. And then, of course, the rover drivers and the engineers can use this data to plan the next day's navigation. So Curiosity navigates only during the day. Because Mars has no atmosphere, it's very, very cold at night and the motors don't operate. So they have to wait for the sun to warm up the motors, and then they will, Curiosity will drive in the middle of the day. Obviously, if you're going to drive, you need power to do so. Now, Curiosity is powered by a plutonium power source. Now, this is actually something that has changed a lot compared to the previous rovers. So the previous rovers, such as Opportunity and Spirit and Sojourner, were all solar powered. As you can see, the solar panels here on the Opportunity. The problem with this is that Mars has extreme dust storms. So when there's a dust storm, the solar panels can become covered in dust, and they no longer receive power from the sun. And then you have to wait for what's known as a cleaning event for the dust to be cleaned off. A cleaning event is probably a fresh wind blowing over. Obviously, they don't know for sure because there's not sufficient information, so they call it a cleaning event, but it's likely to be the fact that the wind blows and removes the dust, and then the solar panels can work again. But this is probably what caused at least Opportunity's mission to end. It was caught in an extremely powerful dust storm in 2018. They lost communications and they never regained communications with it. So the belief is that the dust storm was too large and that the solar panels couldn't be cleaned afterwards. And that was the end of the Opportunity mission. So So this is why possibly not relying on solar panels on an extremely dusty surface such as Mars is possibly going to sort of help Curiosity deal with the extreme dust storms that they might encounter. Another thing that's important when you're driving a robot is the computing power. So space electronics are all radiation hardened, and they have to be space qualified, which is a process that can take around 10 years possibly. So I wanted to kind of give an idea of the kind of computing power on Curiosity, and I was just looking at how my laptop compared to it. My laptop's 5 years old. It's nothing special, and I always complain about it. Like, I complain about how slow it runs. But it turns out that like my laptop has 8 cores, and each of those cores is 20 times faster than the CPU on Curiosity. I also have 16 gigs of RAM, which is a fairly normal amount, and Curiosity has 128 megabytes. So like I have 100 times more RAM in my laptop. Curiosity also has, as a hard drive, either 2 gigs or 4 gigs. It's a bit difficult to see. I said I've had 250 gigs in hard drive, but of course we can also connect multiple terabytes of external data to our computers. So this really gives an idea of how impressive these results are in terms of achieving such successful missions with what seems to us to be a comparatively tiny amount of computing power. So interestingly enough, I mean, Curiosity is 10 years old now, but Perseverance, which is being launched this year, is actually using exactly the same processor that Curiosity is there. It's up to 200 megahertz. So it's getting double the amount of RAM. It's getting 256 megabytes. But once again, like, it's really impressive how these missions operate with levels of computing power that you would consider to not be something that we would expect to have in our laptops or just for like our own computing ability. Now, another really important thing for navigation is being able to see where you are. So Curiosity has quite a number of cameras. There's the ones that we're going to talk about for, I don't know if I have a pointer here, but the cameras that are involved with navigation are the navigation cams, the nav cams, which are up here, the Mast Cam, which are also up high on this, on sort of on the neck head area of Curiosity. And there's also the HAZ cams, the hazard cameras, and they are down low between the wheels at the bottom of the body of Curiosity. So we're going to talk about the nav cams first. So as they are high up off the ground, about 2 meters, this is to give them a good view over the terrain, so they can see over obstacles, they can see over little lumps down into valleys. Now they are there are 2, so they form a stereo pair. So using Stereovision, you can extract a 3D map. So if for those of you who are not maybe so familiar with the how Stereovision works, if you give an example, if you hold your finger up in front of your eyes, and if you close one eye and then the other, you can see that it looks like your finger moves from side to side relative to the background. If you hold your finger further out and do it, your finger will still move from side to side, but a smaller amount. So this means that you can, it means that the 3D position of your finger relates to the offset in your eyes, or in the case of Curiosity, of the cameras. So from the way that a point appears in the 2 separate images from the stereo cameras, you can calculate its 3D position. This means you can extract a 3D map of the surface of Mars. So that means that you can know where the obstacles are, where there are going to be rocks. And this is really important information in terms of navigating safely across the surface. There are also the hazard cams. So the hazard cams are at the bottom of Curiosity's body. They're low down, and they are looking for obstacles immediately around the robot. So they are fisheye cameras. They have a very wide field of view, so they can see any of the obstacles. And they're used to kind of just check the immediate surroundings. There's also the Mast Camera. So the Mast Camera is not specifically for navigation. It's for just general science use, and it's a high resolution camera, and it can see, so you can capture information about what things that are even a kilometer away. And it's also high up on Curiosity, so it has a good view. So this information, while it's not stereo, it is high resolution, so the engineers can zoom in and have a look closely at what they can expect going forward into the future. And this gives them a better ability to plan in the near future if they know where they're going, what they're going to be encountering sort of later on. So those are the main components that appear on the rovers that are used for navigation. There's also a very important component that's not actually on the rovers, and this is the Mars Reconnaissance Orbiter. It's a satellite that's been orbiting the planet of Mars since 2006. So there have actually been satellites orbiting Mars since 2001. But the Reconnaissance Orbiter is particularly, has a particularly high resolution camera that allows it to take photos of the surface of Mars. Now, this is really critical for the navigation, because if you imagine, without having this sort of eye in the sky, the only thing that the rovers and the rover drivers know is what the rover can see in its immediate vicinity. There's very little, aside from a few other images, there's very little information about Mars or about the surface of Mars. So going from having nothing or little, almost no information outside your immediate cameras to being able to capture these high resolution satellite images is a critical part of the successful navigation. So this is the camera that is on the satellite. It's really good. To give you an idea of how good it is, hopefully this image comes out okay on my PDF. If you can see from the top right of the image, there is going down towards the bottom left. If you can't see it, there's a link so you can see it on the actual JPL website. But though, if you can see that, those are the tire tracks of Curiosity. The camera on the satellite is so powerful, it can see the tire tracks of the rover on the surface of Mars. So that's a really useful thing in terms of designing the navigation for the rovers. So those are the components that the rovers use. Now I'd like to talk about how those components are used in the actual navigation process. So first of all, there's no point navigating if you don't have somewhere to go. And so it's the science teams that decide where they want to go. Generally, there's some interesting geology they want to investigate. Again, they can use the information from the satellite camera to select these goals. And then it's the job of the engineers, the robot engineers, the rover drivers to determine if these goals are feasible. So it's a sort of small irony, I suppose, that the most interesting geology on Mars is the places that are hardest to drive on. So Curiosity has a small drill. It can drill into the ground, but it can only drill a few centimeters. So they can't go sort of multiple meters underground. So if the scientists want to see the geology of Mars, they have to find a place where the geology has been exposed. So an example is a crater or the side of a mountain or a cliff, all places which as you can imagine, the rover struggles to drive on. So it just adds an extra challenge to Curiosity, to the rover's mission. Now, I discovered doing this presentation that Mars rover driver is actually a real job. I wish I had known that. I wish I had known that earlier. The job of the rover drivers here on Earth is to analyze the incoming data and plan a path for the rover. So taking the goals and breaking them down into sort of sub goals to the point where they can plan the next step for Curiosity that particular day. So there are different levels of autonomy. This can go from the rover drivers telling the robot exactly where to drive to the complete autonomy where they give the robot goals, waypoint goals, and tell it to plan its own path. There's various trade-offs in terms of speed, in terms of safety that they can do. And so the decisions will depend on various factors in terms of the type of terrain or various things that they want to achieve. Regardless of the level of autonomy, the robot does perform sanity checks. So these sanity checks are things like it checks its motor current. So if the rover gets into some deep sand and gets stuck, it will try and spin its wheels, and because the wheels can't spin in the sand, the motor current will spike. So that's a signal to the system that they are stuck in sand and they should stop spinning their wheels, because of course the more they spin the wheels, the more bogged they are going to get. So that's one of the sanity checks. Accelerometers measure change in accelerometer. So in acceleration, so if the rover is on a hill and starts to slide, the accelerometers will show some change in acceleration, and that's another sign that there's something amiss. And the gyroscopes measure tilt. So of course you don't want the robot to be excessively tilted. So these are all things that it needs to maintain, and regardless of the level of autonomy, the rover can stop its execution at any time if it's getting if these sanity checks tell it that it's getting itself into trouble. So these are the steps that you need to perform navigation. And we'll go through each of them briefly in turn. That you use your cameras to build your 3D model. You then evaluate that the model of the terrain to see whether it's safe or unsafe, or which is the best route to take. You then choose the path. You then drive the path with your sanity checks in place. Then stop and evaluate how you did, and then repeat. So we'll go through, as I said, we'll go through each of these in turn. As I mentioned earlier, the Stereovision can be used to build a 3D map of the environment. So the stereo images scan for points from these points in the image. They build up a mesh of the environment, and you end up with something that looks like this. That looks like showing all the high and low points within the terrain. From that 3D mesh, you perform traversability analysis. So you look for things that are going to be dangerous. So if the robot's going to be highly tilted, if the surface is very rough, and if there's obstacles on which it can get stuck, these are all things that you would look out for, and you evaluate each point in the map to get a map that looks like this. So the idea is that each area of the map is evaluated in terms of what is good and what is bad. So in this animation example, you can see that there's a large rock in the sort of bottom right, and around that it's been marked red. So obviously going over that rock is not such a good idea. There's a slightly smaller rock just in front of the rover's wheels, so that's labeled as yellow. So maybe it's not the ideal path to go, but if it's the only one possible, it can be done with caution. And from this traversability map, you can build paths onto the map and then evaluate each path. So each path is obviously evaluated according to its safety. So you never want the rover to get into an unsafe area. But obviously you also want to get where you want to get to. So there is a measure on how close it gets you to your goal. So if it's taking you towards your goal, that is also evaluated. So the two things are used to determine what the best path is to take. Now I'm going to switch to a movie now. Please bear with me. Sorry, this might take me a moment. And it's just to, okay, wait a sec. Here we go. Now I hope you can see this. I'll start it from the beginning again. Cool.
We can.
We can, great, thank you. So there it's planning its paths. Here we go. Yeah. So, and okay. So this is kind of going to show the whole navigation pipeline working. So you've got the Stereovision, you make your mesh, you, and then you find the path, and you drive the path, and then you repeat the process. That's, well, there, and repeat. Okay, so I will now move back to my, to the presentation. Is that? There we go. So what I would say is this is, you can see hopefully from the movie, you can see the process of making the mesh, building the traversability map, choosing the path, and then you drive the path. Now, each step of that probably happens every half a meter to maybe a meter. So it's a very slow and painstaking process. It is possible for them to, if the rover drivers on Earth do a large amount of analysis, they can maybe let the rover drive for longer if they're sure that the path in front of it is safe. But generally the safest way to go is around half a meter, maybe a meter max, before you stop and evaluate the situation and plan your next step. So that's the navigation process that's used currently on the Curiosity rover. I finally, as I said, I wanted to talk about what is happening now. So this is the Perseverance rover. Now the Perseverance rover is getting brand new science tools on it. They are doing some pretty interesting new experiments. The idea is that they have designed these very sophisticated robot arms to take lots of samples, and they will store the samples, and they're hoping that in future another mission will be able to go to Mars, pick up those samples that Perseverance has captured, and take them back to Earth to be analyzed. So there's some really sophisticated new science tools going on. However, I would say that the navigation system is not really changing much at all. And this is, I think, really like shows the success of the navigation system on Curiosity, on the previous rovers that they're sticking very closely with it. So Perseverance actually has almost the same chassis as Curiosity does. For the first time, they are not making it bigger. So prior to this, Sojourner to Spread an Opportunity to Curiosity got substantially bigger. Perseverance is staying about the same size as Curiosity. And as I said, its navigation system will follow the same basic concepts with some small improvements in the technologies. One thing that is changing, because there's been a bit of a problem on Curiosity, is the wheels. So as I said, the wheels on Curiosity are about 1/2 meter in diameter. They're quite big, and they're made out of aluminium, and this aluminium is less than 1 millimeter thick. So the idea is, like, imagine a Coke can or something even thinner than a Coke can driving on Mars. What has happened is those wheels have got quite ripped up by the rocks. This is more true for Curiosity, I believe, than for Spirit and Opportunity. And I think one of the reasons for that is simply because Curiosity landed in a different part of Mars, and it happens that the terrain there is a lot harder, that the rocks they're going over do not sink into the ground as easily, and so the wheels have had a much harder time and are starting to get ripped up. And it hasn't affected their ability to navigate or their ability to perform the mission, but certainly it means there is a much more caution in terms of how they plan their paths over the terrain to make sure that this doesn't become critical. So the wheels on Perseverance have been slightly redesigned. It's still made of the same material, made of this thin, very, very thin aluminium. But as you can see, the tread has been changed, and the belief here is that this tread might be more robust to the rocks and how they are ripping it up. So that's one minor change that's being made. Another thing that's not actually related to the ground navigation system is the landing system has a small amount of autonomy in it, or contribution from the onboard systems. So the idea is that when Perseverance lands, it will take photos of the landing spot as it descends, and very, very quickly process those images to decide if where it's going to land is safe. And if it's not safe, it has the ability to divert to a different landing location. So as I said, this isn't really related to the ground navigation system, but just a small amount of autonomy there as well. There's one other thing that there's another movie I want to show you just briefly. Let me find it. Okay, now, sorry. So one other thing that is being added to Perseverance is it is getting a friend. It's going, this little helicopter is called Ingenuity, and it is going to be going on board Perseverance in order to fly around and provide higher images of the terrain. So just go back to my presentation. So while I think the Ingenuity helicopter is just kind of cool. It's kind of like a nice kind of awesome thing to be adding on to the mission. How it actually is useful from a navigation point of view is it allows much broader views of the environment. You could send it upwards, just directly up from Perseverance, and it would get higher views of how the terrain looked like. You can even send it forward to get information. So it sort of acts as just another camera for Perseverance, and allows the rover and the rover drivers to have more information in terms of what to expect in their navigation. And of course, with anything, any kind of autonomous or navigation, the more information you have about what's happening, the better it is. I mean, we all know that if you want to get somewhere, walking in a straight line towards where you want to go is not necessarily the fastest way. You know, if there's a locked door between where you want to go, you're going to often going in different directions is a better option. So anything that that the rover can know about what might be coming up can help it navigate to where it's desiring to be much more efficiently. Oh. I am just bear with me a moment. I'm just, as I said, I'm having slight technical difficulties here. Let's try again. Okay. Okay, wait a sec. I will get back to you immediately. Okay, share. Okay, actually, and that is actually the end of my talk. This is just a really, I just really like this picture of Curiosity taking a photo of its tracks that it's left behind on Mars. And I just want to say thank you for joining. I thought this was I think the Mars rovers are a fascinating topic, and I find them really interesting and hope that you do too. And if you want to have any chat or discussion, I'm keen to hear your thoughts.
Dr. Lowry, that was fantastic. Thank you so much.
Thank you.
The videos were amazing. I'm sure everyone else enjoyed them too, right?
I'm glad they were successful. One thing I would say is that NASA has so many resources online in terms of high quality video, high quality images. That certainly makes some, you know, it makes it really interesting to explore what they're doing. And that I've tried to give credit wherever I could. And that also means that, you know, you can look up things you find more interesting afterwards as well, if you're interested.
Oh, fantastic. We have a few questions if you have a little time.
I certainly do. I'm keen to hear people's thoughts.
Fantastic. They're coming in via the chat, just an FYI for the general group. I'm going to read them out to you if that's okay.
Yes, please.
Just as a general rule, we found it works just a little bit more like a traditional Q&A.
Yes.
So, Dr. Lowry, do you see commercial autonomous navigation in vehicles or any other consumer goods having crossover applications with some of the rover technology that you were just speaking on?
Yes. So I'm not clear if you mean that the rover technology can be applied to commercial interests or the other way around. I would say both is true. Oh. Of course. So I guess Mars is in some ways a very extreme environment. The fact that it's been able to navigate autonomously in this very rough terrain, and of course, very robustly, you know, you've got no manual interventions. You can't turn it off and on again or flip it upside down. You know, if it flips upside down, you can't go and fix it. So it has these kind of like lessons in terms of robustness and genuine remote navigation would be useful on plenty of places of commercial application, both on Earth or in space. And I mean, obviously the opposite is true as well. The Mars rover has, you know, like any application, it benefits from the moving forward in technology. So yes, I definitely see that that this could potentially have applications for commercial use, both on Earth, but also, you know, in space as well.
Thank you. How long does the rover think or need to think before each move? I realize there's probably no one answer here.
Yeah, no, that's a very good question, and it's very significant. So the answer is quite a long time. Like it's minutes. It has to take a photo, it has to stop, take a photo, expose the photo for a suitable amount of time that it can get a high quality image. And then with its, I know I went on and on about its glorious 133 megahertz CPU. It takes some minutes to process. So this is autonomous navigation is slow, and this is why. And as I said, it has to stop every half a meter for safety. If the rover drivers, what they did early in Curiosity's mission for the first couple of years, what they tended to do is not give it any autonomy at all. They would get the data, or very little autonomy. They would get the data. The rover drivers on Earth would design a plan, and it would take them the whole day. It would take them 8 to 10 hours of labor to do the plan, and they would send it to a rover, and they send it to the rover, and the rover would execute that pretty much without thinking. And that's a lot faster. That could be a lot faster. The downside is you can only do it out to the limits of visibility. So as soon as you've gone past what the rover drivers were able to see on the cameras, it's better to send Curiosity off on its own because it can keep going. Also, because of the challenges with the wheels getting ripped up, doing a more cautious approach with actually it turns out that doing kind of regular checks in terms of stopping every half a meter and making a decision can actually be safer. But it is a slow process, and a lot of that is related to the fact that the computing power is tiny, well, small compared to what we're used to.
So you touched on the computing power a few times. Could we ask you to expand on why the computing power is just a little bit antiquated?
So I'm not an expert in this area. As I said, there's a certification problem. Well, so the radiation, the equipment has to be radiation hardened for space because there's no atmosphere, so it's exposed. And before it's qualified, just doing the testing to allow it to be certified is a 10-year process. So you can, that is why possibly they don't always use most up to date. As I said, Perseverance is using, as far as I can tell, it seems that Perseverance is using exactly the same as Curiosity. So they've had 10 years for new processes to come along, and they haven't. So I'm not entirely sure why that's the case. I would say, interestingly, I was listening to an engineer who's actually a senior, one of the senior robot engineers for Curiosity, and he made a comment that they almost feel like for the ground navigation, they don't need radiation hardened equipment because it may crash, the CPU may crash, but it doesn't matter because it's on the ground, and they just reboot it, and they might get more quality, they might get better quality performance putting up with the crashes caused by this, rather than having the reliable CPUs. What you need, the radiation hardened ones, is things for the landing and the descent, where obviously computer glitches are not acceptable. That was just a casual, this was just a casual offhand comment by one of the engineers. So I don't know whether that would be a possibility, but that is one suggestion, is that the quality of computers for ground navigation and the quality of computers for orbital aerial navigation don't necessarily have to be the same.
Okay. The questions are coming in thick and heavy, so everyone keep them coming, but we don't want to keep Dr. Lowry for the entire morning that she has left. So one question I'm particularly intrigued on was, how is the trade-off between taking a safer path for the rover versus wanting to actually view or visit some of the more interesting targets? I was especially intrigued on what you said about the exposed geology.
Yes. Now, I'm not 100% sure how that decision is made. Certainly, I think the goals, the desire is obviously to have the robot achieve the goals that are the most interesting geological goals, and in terms of kind of the terrain around Curiosity, I think they have achieved their goals. There was a particularly interesting area called Mount Sharp that they spent some time navigating to. I think there are limitations, but wherever possible, if there's some safety, as long as they can do it with some degree of safety, they will certainly do their best to get there. but I'm not quite sure how those discussions would go between the scientists and the engineers, let us say.
Absolutely. Just one or two more. Thank you for indulging us.
Oh no, it's my pleasure. I could talk about this all day.
Fantastic. So could we. So don't. One of the questions is, has the rover made mistakes inappropriately analyzing what it's seeing, and how far outside its margins can how often does that happen?
So from my understanding, the rover tends to make mistakes on the side of caution, not the other way. There are strict boundaries in which it's allowed to operate. And it tends to, in the early days, it was almost overly cautious. If it saw a small pebble on the ground, it would work its way carefully around the small pebble. Now that's not ideal because that really limits. Mars is very pebbly. You have to at some point go over. So you have to balance out the margins of that. There have definitely been mistakes. I mentioned the problem with the motor current, like measuring the motor current to make sure you're not stuck. That was actually implemented because Opportunity got stuck. It got stuck in some sand. It didn't check its motor current at that time because it was an earlier generation, and it just kept on spinning its wheels and got more and more bogged. It took 2 months to get it out of that sand trap. So I guess there's been a learning process in terms of it's a good what to check in terms of these sanity checks and these safety checks. But it's certainly, it is quite impressive that all the missions have been so successful, given the fact that they are learning how to navigate on Mars at the same time as doing it.
Fantastic. Could you expand a little bit more on the Ingenuity helicopter? How does it communicate with the rover? It's a great video, by the way.
It was a great video. I had to share that one just because I think it's a super cool piece of technology. I'm not an expert on on Ingenuity. That's a very interesting question. I don't have any details about how it communicates with the rover, whether it's line of sight, whether it has to see the rover to be able to communicate, or whether it has other communication on board. That is actually a very interesting question. But yes, no, I'm sorry, I can't answer.
We do have one more question to do with the 3D mapping from the optical cameras. There was a question on the possible use of active LiDAR-based approaches. Was there a reason why that wasn't an option in this case?
So that's also a very, very interesting question. Certainly here on Earth, LiDAR is essentially the number one choice for robots. I use vision, but that's until recently has certainly been the exception. I guess I don't know the answer for sure, but one of the problems might be power. So cameras are much, much lower power than LiDAR because of course they're not sending out active light themselves, and they're much lighter. Although Curiosity, that's not so much of a problem because it is quite large anyway. But certainly I would say power requirements might restrict LiDAR. Otherwise, yes, LiDAR is, in terms of building 3D maps, using active sensing is a much more effective way to do it than using Stereovision. So it's interesting that they haven't chosen to do that. And my guess would be power requirements only.
That makes sense. Okay. Do we have any final questions? Fantastic questions tonight, really technical and very pointed.
Sorry to interrupt. Can I just say something? I've just been thinking about that LiDAR question. One other thing I would say in terms of why LiDAR might not have been chosen for that is that up till very, very recently and still now, spinning LiDAR is the most common. So you have only a couple of lasers and you spin, and moving parts are something that you don't want on a robot that you can't change, that you can't do maintenance on. that's changing. You're getting more static lasers, that LiDAR, that don't spin, but just saying that might have been another consideration in that process. Sorry to interrupt. Let me hand back to you.
No, that was super important and interesting. I'm really happy that you added that. Thank you. So everyone, if we could very much, I'm sure you'll all join me in thanking Dr. Lowry for this evening. Fantastic chat. If I could find my little reactions thing, I would give there we go, clap. Thank you so much. It's been a really interesting evening. And I hope that if you're interested, you could, in the future, maybe come and give us an update on
yes
efforts.
Well, Perseverance should be landing in February 2021, so I think there's going to be a new wave of interest in Mars rovers. I would expect, hopefully, and so yeah, I'll be interested to see what's happening going forward too. So yeah, so thank you very much for your time, everyone. It's been it's been a pleasure.
Oh, and for the rest of the group, who hopefully can still see me and hear me, there we go. Please check out our MeetUp, our Facebook group, and please stand by for more information on our monthly talks going forward. We're getting some really fantastic speakers. We're going to continue the Zoom format probably for a few more months. We've gotten a lot of national interest, and that's allowed us to sort of broaden our geographic range, as it were. We welcome any suggestions on speakers. Once we go back to an actual proper meetup, we definitely welcome recommendations on locations. And please do not be shy. Reach out on the Facebook page, reach out on the meetup page. Many thanks again to Dr. Lowry. Many thanks to our space-based crew. And if no one has any further comments, thank you, everyone.
Thank you.